Sorcha. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Matthew Holman with us today. Hi, Matt.
Hi, Frank. Thanks for inviting me.
Sure. Well, thanks for agreeing to talk about your very awesome article, which we will get to here in a second. It is October 2nd of 2025 as we record this. And Matt, what is your geolocation?
I am in Cambridge, Massachusetts at the Harvard Smithsonian Center for Astrophysics.
And that tree over your shoulder is not turning yellow and red quite yet. So I don't know if fall is quite in the area in Cambridge yet.
It is cooling off, but the
Okay.
leaves haven't fallen.
Okay, good, good, good. But give it another couple of weeks is probably when they'll get their real color and all that.
Mhm.
So I'm in Phoenix, and we are definitely cooling down. That's, of course, a relative term when you're in the Sonoran Desert. We'll still hit 95, 96 today, but the air is drying out, and we're definitely, past the peak heat. So I'm thankful for that cooling post-equinox temperature is very cool. And Matt, what do you like to do for research?
Well, my background is in solar system dynamics. So kind of for my whole career, I've been developing algorithms to, integrate the n-body problem to
Yes.
find things in the solar system to study planets around other stars. I like to work at the interface between theory and observation,
Cool.
right? And kind of all of the research that I do, it might be on the Kuiper Belt or exoplanets or something like that has about something to do with dynamics and data.
Very nice. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Sorcha, optimized solar system ephemeris generation. And Matt, take us away.
Yeah. So Sorcha is a solar system survey simulator
Hmm?
that was built with Rubin's legacy survey of space and time in mind. Before
Okay.
I dive into this, I want to highlight some of the co-authors and collaborators who made this possible.
Yeah.
I'm going to first highlight Meg Schwam, who is really the leader of the Sorcha team
Hmm.
and worked with Steph Merritt, a graduate student at the time. The people that I have worked with a lot on this are Pedro Bernardinelli, who was at the University of Washington, still is, and is about to move home to Brazil for a permanent position there.
Cool. Nice.
I also want to highlight Mario Juric, who's really the lead of the solar system work on Rubin, but also Drew Oldag and Max West. They were the software engineers that did a lot of the work as part of the Link Frameworks team. So Link
Okay.
is a group based in near University of Washington.
Hmm.
They help people turn their software ideas into a real product.
Cool. Very good. All right. Yeah, that's quite the international crew there. So very good. Very nice. Good shout out. Good shout out. Okay, let's go ahead and get into it.
Yeah, so a survey simulation, just so people have a sense of what that's about, is if suppose you've got some specialized equipment like the Rubin Observatory and it's a large camera, and you can take a lot of images of the sky over the course of 10 years, and you're looking for solar system objects in this case. We're looking for things that are moving. They might be near-Earth asteroids, they may be distant Kuiper Belt objects.
Hmm.
You carry out your survey and you find some number of things, and if you just look at the number of things that you found, you don't know whether that's you found all that there are to find
Okay,
or a small fraction of a much bigger population.
fair enough.
And as astronomers, we face this kind of thing where we're trying to take out the biases of our surveys and experiments.
Yes.
And kind of what's become sort of the gold standard for doing this is to just simulate the whole process.
Hmm.
And in this case, we start with a set of orbits, a hypothesized set of orbits of solar system objects of different types,
Hmm.
and we want to simulate of those objects, when would they appear in an exposure? And so we have some survey pattern that's been developed for Rubin and lots of other different surveys, and we want to know, okay, which of these asteroids or Kuiper Belt objects are going to appear in which exposure, and are they going to be bright enough to detect,
Right.
and all of the steps. And because it's
Cool.
really hard to kind of do the reverse engineer it, where you just say, okay, we
Ye-
find these objects, and then we say, let's try to go backward from there. It's easier to go forward. We're a population and say, okay, does this match the observations?
Cool.
So that's really what we're after there, and that's what Sorka is designed to do. And there's a
Nice.
couple of big parts to Sorka, and they divide kind of cleanly into the part that we're focusing on here, which has to do with the orbits.
Okay.
And then there's a second part of, okay, if this thing appears anywhere close to some exposure that the survey is going to take, did you actually make the detection?
Yes. Okay.
Did the detection fall in chip gaps, or did it hit live silicon? And if so, was it bright enough to detect? So
Okay.
those are the two parts, the orbits, and then sort of the kind of post-processing phase.
Good. I'm with you. I'm with you.
Um, so my task was really to make that first part computationally feasible.
Right. Make it boom.
Yep. There's going to be a huge amount of data from Rubin. As I said, it's a nominally a 10-year survey. It's going to cover, you know, roughly half the sky, probably more. It's going to increase the number of solar system objects that we know about by, say, a factor of 5 to 10.
Nice.
And so there will be a huge number of objects discovered and a large number of what we call visits, exposures to a particular place in the sky. A
Yeah.
couple of maybe 2 million visits over the course of 10 years. So, so you can imagine it's computationally challenging if you start with
Yep.
a population of millions of objects and you have, millions of exposures. How do you do that?
Yes.
So
Efficient.
that's what we're really after here.
Cool. Very good. Okay. I'm with you.
Other people have done this kind of work over the years, and I've highlighted a few. Jean-Marc Petit was part of the AAS group, developed a survey simulator. Shantanu Naidu has developed something. He's at JPL.
Yep.
Basically, anytime you do a big survey, you kind of have to come up with a simulator in order to be able to analyze and make sense of your data.
Okay.
One of the things that's really different about uh, Rubin and its LSST
Uh-huh.
is that there's really not a clean separation between the fields you use to discover the objects
Okay.
and the fields you use to kind of follow them up.
Okay.
So kind of what has happened kind of by design in other surveys is to sort of declare, okay, we're going to do this, what we call, the discovery fields. On these nights, we're going to
Yes.
look at these pieces of sky and find objects in those fields. And
Mhm.
then once we find them, we're going to track them and we're going to try to track all of them.
Yes. Okay.
But Rubin and the legacy survey of space and time is different. It's spread out over 10 years, and it's not divided up into, okay, these are the discovery fields and these are the follow-up fields. It's just one big survey.
Right.
So you instead, if you just declared that a certain subset were your discovery fields, the simulation would be a little bit easier because you just have to say, these orbits, did they appear in these fields on these nights?
Right.
Where we need to say, okay, did we, how many times did we see this object? Did we see it enough times to discover it, to be able to link the dots of this moving object and say, okay, these all go together and this is its orbit.
Beep, beep, beep. Yes.
So it's more challenging.
Mhm.
Um, Yeah, so that's what, Sorka is really about, and it's trying to do a really high fidelity job with this. When I say high fidelity, I mean the orbits really are simulated to the best of our knowledge of the physics, which is quite high, and also our understanding of the telescope and the focal plane and all of that.
Yes,
So that if we want to analyze our data based on a simulator, we want our simulator to be as close to reality as possible.
indeed.
So let's, I guess, scroll on a little bit more.
Okay, let's go down.
So,
Fully from ours.
yeah, let's go to the simple ephemeris generation section. Let's just use that to kind of guide us as I did in the paper.
Okay.
Um, so another one thing that sort of distinguishes uh, searches for solar system objects and simulations is that you can't just sort of, the objects move. That's the punchline. And not only that, but light time matters a lot. I mean, we're astronomers. We know light, takes time to get from point A to point B.
Sure.
It matters a lot when you're looking for a moving object
Yes.
because when you see the light from a moving object, you're seeing where that object was
Uh-huh.
lifetime in the past. By lifetime, I mean the time it took to get from, where that light was either emitted or reflected from the object
Huh?
to to the observatory.
Right.
And if you look at this equation here, that you've highlighted, so I'm calling, well, you can go to equation one.
Yeah, let's just do, there we
Yeah,
go.
just do that one. That's great. Where you were before.
Uh-huh.
Either one. Okay. Sorry.
Yeah.
Sorry.
All good.
Um,
We'll do both.
yeah, so this equation is really this is just saying the direction to the object. We're going to have a unit vector, and
Yep.
that's a vector from the observatory, where the telescope is at a particular time t, in the direction of where the object was at time t minus the light time.
Correct. Yes.
And the equation for solving for delta t it's an implicit equation.
Uh-huh.
You have to know delta t to be able to figure out, where the object was, and you have to have that in order to figure out what delta t was.
Right.
And this is an old problem with an easy solution.
Mm-hmm.
And the solution is just iterate. The
Yes.
solution is basically let's let's first assume that light takes no time to travel.
Okay. That's a
And that where we
observatory.
see the object, when we see it now, it's where it is now.
Mm-hmm.
We use that answer to say, okay, then what is the distance between that object and the observatory?
Yes.
And divide by the speed of light and say, okay, this is how many minutes it took to get from there to here. Use that answer and plug it in again and say, okay, this is where it was, for that, assuming that light time, compute a new light time, keep plugging it in. And it takes, the answer is 3 or 4 iterations. It just, it's,
Urges
it,
well.
it converges well. In our solar system, things can be, it's 8 minutes per astronomical unit. So things are
Yes.
minutes to hours away.
Mm-hmm.
Um, so but it's really important because let me get you for scale, an asteroid observed from the Earth is going to appear to move 30 to 40 arc seconds per hour.
Okay. All right.
So in 20 or 30 minutes, it will move many, many arc seconds.
Yes.
It'll move hundreds of arc seconds. So if you don't account for light time, you're always going to get the wrong answer. And when your image, when you can locate something to fractions of an arc second, like tenths or even milli-arc seconds,
Oh, yeah.
you're going to get a very wrong answer if you don't include light time.
Right.
Okay, so let's look at equation one again, just sort of highlight, kind of give a roadmap of what we're going to do.
Sure.
Um, so the parts in here are, the R, the boldface R.
Mm-hmm.
So you're lingering over our observatory. So I'll start. You just stop wherever, and I'll talk about
Let's
it.
talk about our observe
Okay, so that is where the observatory is.
on the surface of the Earth.
And it's where the observatory is with respect to the origin of our reference frame.
Huh?
And just, we're going to use barycentric equatorial reference frame, and I'll explain why I did that later. So
Okay.
that's just where the observatory is
Hmm.
at the time of the observations, time t.
Okay.
The other boldface R is the position of the object, and that's the position of the object at, time corrected for light time.
Correct. Yep.
And then the denominator of that is just the length that turns it into a unit vector.
Right.
So
Unit state vector. Mhm.
yeah, so you can see like basically this outlines the things we need to do well. Just to calculate where a particular object is on the sky, we need to be able to figure out its position vector with respect to, say, our barycenter of the solar system. We
Hmm.
need to know where the observatory is, and we need to know that very precisely. And we need to be able to do this light time correction.
Cool. Very good. And I'm just going to give a shout out to the GitHub and documentation. Check that out, people. It's good.
Okay, so let's roll along a little bit.
Hmm.
So we talked about those, so here I'm saying like here are the steps. Figure out where the observatory is. Uh, convert so you have some initial set of orbits, convert that into some initial conditions, some position and velocity that you can numerically integrate.
Yes.
Uh, you know, figure out, from that's, at some initial time, then numerically integrate it to the time near the time of observation, and then do the light time correction.
Yes.
So I'll just kind of go through some of these steps.
Cool.
And the observatory location, I like to joke that if you look at the first three chapters of, not so old astronomy textbooks,
Okay.
or a lot of it is just about where is the observatory. All the
Hmm.
stuff about hour angle and, all these calculations you do,
Hmm.
where are you on the base of the Earth? That, this very elaborate, detailed stuff. But there are tools in Python now
Nice.
that incredibly easy. Uh,
Hmm.
you can basically rely on things that the Jet Propulsion Laboratory and other groups have provided that can tell you uh, what the orientation of the Earth is in space. And you can also look things up through the Minor Planet Center and say, where is the observatory with respect to the center of the Earth?
Hmm.
And you can take these tools and say, okay, what's the rotation matrix to go from this time to that time, and just like where you are on the Earth, where is the center of the Earth with respect to this the center mass of the solar system.
Uh-huh.
So it becomes a lot easier in the sense that there are good tools to allow you to do this really
Nice.
precisely. So
Good.
that's a step here.
I'm with you. Hmm.
And you want to do when you do that, you want to be really consistent so that the kind of tools that we're using to figure out where the observatory is are consistent with the tools we're going to later use to say where are the planets and
Uh-huh.
everything else is. So I think we can probably scroll along.
Okay, so we've got our observatory. Now we need some initial conditions. Yes.
Yeah. So normally people are going to, if they have an orbit population, they're going to use orbital elements.
Hmm.
They're going to say, here's a semi-major axis and eccentricity and inclination of this population.
Yes.
When we do a numerical integration, we want a position vector and a velocity vector.
Yes.
We have computers now, so we don't have to do things strictly in orbital elements.
Right.
So, but that's, what this section is about is a kind of a robust routines that can take any kind of orbit, uh, highlighting interstellar orbits, right? You can have something that is
For example.
highly eccentric, perhaps unbound to the sun,
Right.
and it's going to generically, go from orbital elements to a position and velocity vector.
Yes.
So
Cool.
that's kind of the heart of that, and it's
Want it to be really robust.
really but robust, and it harkens back to the old stuff like this, these universal variables that Stump
I'm
developed.
with you. I'm with you. Yeah, yeah.
Yeah, I mean, so and Danby is this like you know one of my favorite books because it shows you how to
Exactly
do
how to do
all
it.
of these things.
Yes. Hmm.
And so yeah, part of this package is just making sure that we've got that in hand and we can go back and forth from from orbital elements in different formats to position velocity vector, from position velocity vector back to orbital elements in different formats.
Cool. Beautiful.
And then, we talked about, various ways to, tests we did to make sure that we got that right.
Hmm.
And, we did
Very
various,
nice.
tests
You were
with
getting down to at least machine precision at double precision.
that.
Anyway,
That's the goal, is like to make sure that to the extent possible
limits
we're
of the arithmetic.
yeah, yeah. And so we, done a few tests with, my favorite asteroids, 3666 Holman, uh,
Beautiful.
and, Oumuamua, and
Yes, yes, yes.
it's an interstellar object and a Kuiper Belt object, and just
Mm.
show that we can get these, we can do this correctly and to, small enough error that no measurement is going to,
Pick that up.
yeah,
Right.
pick that up.
That
Yeah.
one. Right. So JPL Horizon is another good one to check out. Nice. Good. Hmm.
So we, sort of on the roadmap, we've talked about where the observatory is.
Uh-huh.
We've talked about how to, convert our, initial conditions, uh, and we're going to talk about, integrating those
Iterating.
initial conditions.
Yes. Let's do talk
Um,
about assist.
so assist is something that I developed a couple of years ago, and I'll give you some background on that.
Yes, please.
So JPL, many of us have used the JPL Horizons
Mm.
package, right? It's really a wonderful thing that can tell you, this object in the solar system, where is it observed from any whatever observatory, different times, different formats,
Mhm.
rising and setting times, all kinds of really useful stuff if you're interested in solar system astronomy,
Yep.
observational solar system astronomy. Um, but it is not an open source package.
Correct.
It's a web interface, and you can't get at the back end of it.
Correct.
That means, it's still incredibly useful, but you can't do your own simulations with it.
Correct.
So I decided to make an open source version of that.
Beautiful. Beautiful.
And really the timing of it worked out really well because a few
Mhm.
pieces really
Yep.
became available. So one of them is Rebound, which is something developed primarily by Hanno Rhein at University of Toronto. It's a
Yes.
suite of solar system integrators, and it's a really nice package that's written in C in the back end and is Python accessible. The front end. And it has one particular integrator in there that they call IAS 15.
Yes.
I'll talk about that later, why that ends up being really good because it's flexible, it has a variable time step.
Yes.
It's really and it's extensible. You can add things to it. So um, and then the other piece that came together was um, we suppose we wanted to integrate the orbit of a test particle, some asteroid in the field of our solar system. We
Hmm.
need to know where the sun, Earth, Moon, other planets, perturbing asteroids are
Yes.
as a function of time to be able to numerically integrate those equations of motion.
Yes.
Every time we want to say, okay, here's the object at this time, what's its acceleration?
Hmm.
And so this is where a guy named Rob Warwick, who's the University of Western Ontario,
Uh-huh.
some really nice routines that can very rapidly evaluate what are called the JPL spice kernels. These are
Yes.
binary files that you can use to tell you where the planets are, at any particular time. So he made that really, really fast uh,
Cool. Good.
and memory efficient. So
Yeah.
we put it together. Um, Meaning we can tell where all the perturbers are at any time efficiently
Okay.
and
Yes.
have a way to efficiently integrate them with this IS-15 integrator.
Hmm.
And okay, so the folks at JPL can't share code, but they can share tables of numbers.
Yes.
So what I did with Davide Fornacchia at JPL is we picked an asteroid and a time, and and all of the terms in the equations of motion, you
Hmm.
know, acceleration due to all the planets, terms from GR, gravitational harmonics of the sun and the Earth,
Yep.
everything that is in the JPL integrator
Yes.
behind horizons. And that's not any secret knowledge. That's
No, you can
published,
get
right?
from papers. Yeah,
And
yeah.
there's no inventing of physics. It's just implement these things that are known.
Hmm.
And I coded all of that up and compared my result to the table of numbers and made sure that they agree to machine precision.
Nice.
And then, take that and use the IS-15 integrator.
Hmm.
But one of the things that's really neat about IS-15 and rebound in general is that you can add terms to your equations of motion. You can have like a black box external function when you say, okay, here's the acceleration on this object. Oh, and by the way, give me a little bit from this other routine.
Okay. Okay.
So what Assist is doing is building an extra routine that does all of that. It says,
Cool.
okay, you've got this small body. This is the acceleration due
Hmm.
to the solar system.
Nice.
And it just hands it back to IS-15. So that's all, yeah, it's on GitHub. That's been thoroughly tested and it's getting pretty widely used.
Yes. Very nice. Beautiful.
And I'll get to in a little bit why there's a, particularly fascinating and useful characteristics of this IS-15 integrator that we can use to help solve the light time iteration.
Yes. Cool. Okay. Hmm.
Okay, let's scroll a little bit.
Okay. So we got
Um,
IS-15.
so mostly this is about, oh yeah, I'll go ahead and talk about that.
Yeah.
So what the IS-15 integrator does is something called a predictor corrector method, meaning it like, you're trying to get from time t to time t plus some, delta t, some time step. You're trying to get t1.
Hmm.
Uh, and you do, various numerical manipulations and steps. And the way this one in particular works is you you estimate what the acceleration is at a set of carefully selected points on the time step interval.
Yes.
Something like, a Chebyshev polynomial interpolation, something that allows you to really precisely
Yeah.
uh, approximate a function over some interval.
I'm with you. Hmm.
So you've got this set of integrate these acceleration estimates and a polynomial that fits those, and you integrate that polynomial twice. Once to get the velocity, twice to get the positions. You use those new positions to update your accelerations
Uh-huh.
because the accelerations just have to do with relative positions among the masses, and you get an update on that, and you keep doing that, acceleration to velocity to position to acceleration to velocity to position
Hmm.
until it converges.
Yes.
And then normally what you do is use that to say, okay, where was the position and velocity at the end of the interval, right? You're trying to take a time step, and usually you say, I'm done with that.
Right. But
But you actually have the ability to then determine where this object was anywhere in that interval
yes.
just by evaluating the polynomial.
Uh-huh.
Evaluating a polynomial is way, way cheaper than doing the numerical integration.
Absolutely.
And when you, for the other feature that's really nice is that IS-15 will tell you what's the good time step based on what it already did. So it'll suggest, okay, 10 days worked so far, 15 might be better.
5:15.
And so as you numerically integrate, the time step will go up and down as needed.
Yes.
When the asteroid, say, is having a close encounter to Earth, it'll wind down the time step really small so that it can handle that and get the right answer.
Yes.
So it means that if you are doing a survey simulation and you need to know where the object is, like frequently,
Yes.
So often surveys aren't like taking a picture every 10 or 15 days. They're taking several in a night and maybe the next night and 2 nights later. So you
Right.
often need to know the positions more frequently, on a spacing that's small compared to a time step,
Right.
which might be 10 or 15 days. So
Cool.
that's one of the optimizations is that
Right.
if you keep track of that information, you can do these simulations much more efficiently because you don't have to do as much computation.
Correct. You're just evaluating polynomials. Very
Yeah.
nice.
So
Cool.
we're combining that you know assist, and then we're going to exploit this feature of IAS 15 to do. We're going to doing a it also helps us
Oh
with the
yeah.
light iteration, right?
Yes.
Because we
Yes.
just that's the light time is going to be tens of minutes, and instead of having to keep integrating to zero in on that, we just evaluate this polynomials.
Mm-hmm. Let's see.
Let's
Put a
keep.
number on that. That'll crank things up by 2 to 4 by doing that. Good.
Yep.
Good, good, good.
So that, and I've talked a little bit more about the light time iteration here.
Okay.
I think I
Hmm.
think I've covered that.
Okay, simple, reliable. Yeah. Few iterations. I'm with you there. Ooh. Uh,
Yeah. So that's the kind of thing is uh, you can make these things a lot more efficient if you don't actually uh, test for convergence. You just provide a number,
do three.
the number shall be three, and
Right.
you
Right.
just in fact that's it's
Just
faster to just provide enough iterations in general than to keep checking.
right, because otherwise you got if statements going on, you got to decide whether you're looping back, la 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 la. That all adds
Yeah,
up.
so
So
we're gonna make sure that it's gonna be easily parallelized, and we're not gonna have a lot of branches in the code.
exactly. Perfect. Perfect. And we got some state vector stuff here. Let's cover that a little bit. Okay, table one.
Yeah, so table one is really just testing,
Mm-hmm.
uh, our accuracy, or the difference between what we get, light time corrected, position state vectors between what we get with Sorcha using assist and JPL,
Cool. R
and the
dot.
JPL horizons.
A couple of
And if
little
you
elements there. Mm-hmm.
so the
Alpha deck.
good thing there is that we're for most objects where the orbits are really well known, we're tens of micro arc seconds different, right? They are functionally the same.
Very cool.
And
Except
that
when you have non-gravitational stuff, which you're not going to get. Right.
exactly. So right now, Assist does have the capacity to do non-gravitational accelerations. That is not yet used within Sorca.
Yeah.
But
Okay.
that's something for the future.
I'm with you. Oh, we'll come back to that. Okay. Mm-hmm.
But really what we wanted to be able to say is just that it's functionally equivalent to JPL
JPL,
Horizons, which is the kind of current gold standard.
gold standard.
We
Yeah.
don't have to have a conversation about, okay, we didn't make a design choice to let's use somewhat lower fidelity ephemerides just to speed the whole thing up. They are, top-notch ephemeris positions. We don't have to worry about did we cut a corner that affects our results.
Yeah. Beautiful. Beautiful. Okay. Good. That's our
Yeah, so
validation.
then we went through this validation, make sure that it works on the small scale. And
Mm-hmm.
then we're going to shift gears. Like, okay, we know how to do one of them.
Now let's
How,
do a lot
how
of
do you do millions of them
them.
with
Yeah.
millions of exposures?
There you go. Art.
And I'm going to try to get right to the punchline, which is uh, if you could look at the whole sky one night and you look the next night, the objects really haven't moved that far.
Okay.
So the brute force way of doing the problem is taking all of your orbits, and every time you have an exposure, you integrate all of your orbits to the
Mm,
top of that exposure, do
mm.
the time correction, see where those things appear on the sky from the perspective of the observatory, see
Yes.
which ones fall within a certain angular radius of the center of the exposure. That's really slow.
Yes.
And it's totally unnecessary because if suppose I'm looking over here, I don't need to worry about the asteroids that are behind me.
Okay.
right? I only need to look at the ones that could plausibly be in my exposure.
Right. Correct.
So the idea is to figure out on a roughly nightly basis exactly where everything is.
Uh-huh.
And then
Uh-huh.
when you have a new exposure, you say, okay, which ones are close? Like so we're going to have like what we call a picket fence of times, like every midnight, every night, where's everything? And no, an exposure comes in and it's not going to be midnight. It's going to be some other time. And we're going to say, okay, well, which ones were close at midnight?
Okay.
And we're going to allow a buffer around our exposure, a big enough buffer that, nothing's going to, we're going to be able to get everything that could possibly end up in our exposure.
Cool. That's a lot smaller problem. Hmm.
Yeah. And then we're going to
Hmm.
precisely calculate the positions for those objects.
Nice.
And often it's actually going to be not hard to do because we can do this polynomial evaluation thing.
Right. Right.
Um,
Integration gets fast.
but that's the gist of it. And so to give you a sense of how big of a speed up that can be,
Cool.
there are 40,000 square degrees in the sky.
Okay. Yes.
And Rubin's camera is 10 square degrees.
Hmm.
So if you don't have, there's a factor of 1,000 speed up available to you if you only need to look at the things that, are close to the exposure.
There you go. Okay. Good. Nice.
So we've already gotten a
At
speed up
scale.
by using a fast integrator and by, using this polynomial evaluation thing. But
Uh-huh.
now we're getting really serious where, on the large scale, we want to just, keep track of where everything is roughly so we can just sort of clean up exactly what we need.
Yes.
And we use, we've used this heel pix tessellation, and that's really a way to keep track of where things are in the sky.
Uh-huh.
That's, enumerated buckets, enumerated tiles that cover the sky. And so we figure out at midnight from Rubin, where are all of our objects, where do they appear, and put them in their heel pix buckets.
Yes.
And then we take an exposure and we say, okay, which heel pix regions does that exposure cover
Hmm.
with some buffer? Take out yeah, get the objects that are in those buckets, get their precise positions, and figure out which ones really did land in the exposure.
There you go. I'm with you. Hmm.
So that's the gist of that. And then, for people who are in the know about heel pix, there's a scale. You can cut up the sky into buckets that are, of different scales. You can, they're little squares or diamonds, and
Hmm.
you can make them half as small, 4 times, 8 times. And
Whatever.
so there's going to be a design choice of how small our tiles do we want.
Okay.
And it's just a trade-off of you want you don't want your buckets to be small, so small that most of them are empty,
True.
but you don't want them to be so big that it's a lot bigger than the field of view of your camera.
There you go. Clear.
Otherwise, you're going to be doing work you don't need to do.
Correct.
So I think we can probably scroll on to the next section here.
Example. Let's talk about this figure.
So this is not my favorite figure, but it's the only figure in the paper.
That's right.
So, so we'll go with it.
We will go with this one. Okay, we got kind of all going here. We got heel picks, we got tiles. Let's go.
So we're, this grid here are going to be, basically represent our heel picks tiles.
Yes.
And they're diamonds just because that's the way they're oriented on this sphere. And but what we're going to do with the ephemeris generation stuff is we've calculated on a ongoing nightly basis
Hmm.
where everything is. And I say an ongoing nightly basis because we're doing a survey simulation and we get to choose the order we're doing it in.
Okay.
We happen to do it in you pick a time, the time, you just declare that, whatever is your sort of the origin of your time, and you can look forward from that or backward from that. And the advantage is you don't have to store a lot of stuff. You
Yeah.
just say, okay, let's say for last night, tonight, and tomorrow, where is everything?
Okay.
And I know precisely where those are, and I can do a little polynomial fit to do a little bit better.
Yes.
So that the reason why we would do that is that some things really do move very quickly. So what this diagram is showing is that the green circle is, and is say the Rubin field of view.
Yes. Okay.
And we can maybe, maybe with a little extra buffer on it, and we sort of know, okay, these are the objects, these are the heel pixtiles that have any object, had an object in them at midnight, and then we clean them up and we see which ones are actually in the field of view. That's what that diagram is showing.
I'm
The,
with you.
the tricky thing is that, okay, most of the time it's enough to know where the object was at midnight. That is often enough. If you just say, okay, where was it at midnight? Let me give I don't know, 10 or 20 arc minute buffer around that.
Okay.
I'm not ever going to lose any objects,
Right.
except for near Earth objects.
Meow.
Yeah, they're screaming along. They can go from this side of the sky to that side of the sky in days if they are coming particularly close to the Earth.
Yes.
We don't want to lose those because that's one of the interesting areas for Rubin. And so that's where we sort of had done this work of let's instead of taking just tonight, let's take last night, tonight, and tomorrow night. You could make this arbitrarily complicated,
Okay.
where you can then, really have a better, you can find the ones that are zooming across the sky and say, okay, we know this thing would have gone through the field of view, went through the field of view sometime during this night.
Yes. Okay.
And then you can basically add that one to your list of these are the ones that we want to follow up. We want to make sure.
Yes.
That's all it's doing is the process is to start with everything, figure out what are your likely candidates, zero in on the likely candidates and find out which ones really are going to land in the field of view.
I'm with you. Hmm.
So I guess we can proceed.
Okay. Let's see. Where were we? Oh, yeah. We were doing the high level heel picks. Okay. Very good. Yes.
So I think this is just kind of describing that process of
Right.
start with, orbits and, figure out where they are on a, in an, 2-day interval of last night, tonight, and tomorrow.
Nope.
Keep track of all of that and check to see which objects actually fall within the field of view.
Cool. Okay.
And that's kind of like other than testing, kind of my job is done then, in the sense that this part of Sorcha is about taking a set of orbits and figuring out which of those would land within a radius of a particular point on the sky
Yes.
as we go through a sequence of those exposures and do it efficiently.
Okay.
The next part is going to say, okay, these are the ones that fell within that radius. Let's see whether they hit live silicon or chip gaps and if they hit live silicon, were they, bright enough? That's the downstate,
Yes.
downstream thing.
Yes. I'm with you.
Let's see.
Okay. Hmm.
So that there are, design trade-offs of, okay, I picked tonight and last night and tomorrow, that like one, 2-day time span
Yes.
because it is a natural fit to the way astronomers work. We observe it at, night, and this is, Sorcha's or Rubin is ground-based, so we have to stick to the it's dark at night kind of problem rather than, in space where you can kind of observe all the time.
Yes.
But kind of that interval uh, that is a tunable thing. So then, in terms of validation, we want to make sure that if we start with a set of orbits and we use this ephemeris generation package within Sorcha, that we get the right answer. I
Yes.
mean, so we know that we can get the right ephemeris positions. That's already been tested.
Yep.
What we want to make sure is that we're not missing something that should actually be in the field of view,
Aha. Okay.
right? We're less worried about at this stage about uh, I would say a false positive in the
Yeah.
sense of you start with an orbit and you think it's in the field of view, but then when you look, it's not actually
Right
there.
there.
Okay, a false negative where it really is there, but we've said no, it's
Yeah.
not. That's the problem. So that's what the validation is about, is just making sure we're not missing missing anything. And it's the focus is really about near Earth asteroids. Um,
Mm.
and we, turn the knobs to make sure that that works. We're not missing
Right.
things.
Yeah, we are got sufficient sensitivity in all cases. Very cool. Okay. Nice. Okay, we even got some timings here on particular machines if people are interested in checking that out. Okay. So it sounds perfect, but of course, there must be some caveats.
Yes, there are always caveats. So, well, as I say in that first one, that for really fast moving objects,
Mm.
it's difficult to really prove correctness in all cases. We can do a lot of simulations and say, we didn't miss any of them, but we can't actually prove that mathematically that we can demonstrate it
Oh,
through
right.
simulations, but we cannot say,
Right.
this is absolutely correct.
Okay, let's take a look at table two. Table two.
That's not actually that was only important because somebody requested to have that table.
I wonder who that somebody might have been, but okay.
Yeah, so that's so assist includes the sun, planets, major these 16 massive asteroids,
Uh,
and that's in the model, and somebody insisted on having a table of those.
oh, that referee. Okay.
Oh, that referee. Yep.
Oh, that referee. Okay.
Yep.
Okay,
So,
cool.
yeah, so the other caveats are, well, if one thing is if you use one of the asteroids that's actually in the integration model, you're going to get the wrong answer because you're putting something on top of another mass, and so that's a caveat is don't use integrate Ceres and Vesta and Pallas uh, with this without being a little careful.
Yes. Okay. Good.
Um,
Good, good.
and then so right now, I mean, assist can do non-gravitational
Mm.
accelerations due to, outgassing and other things like that, but that's not used in Sorcha at the moment. So if you really want to do comets and other things that may be undergoing non-gravitational accelerations, there's some work to be done.
Yes. Which
Uh,
we'll get to in a bit. Okay. Okay. Very cool.
and we have also are using, we're just assuming we know the orbits precisely. So
Yes.
orbits are never known to, infinite
Sorry.
precision.
Yeah, yeah. Okay.
So when we're predicting where an object is, there's some uncertainty associated with that. And that's something we are working on. We can quantify orbital uncertainty and how that translates into uncertainty on the sky and where it's going to appear.
Yes.
So that's something to it's just a statement that it doesn't do that yet, but it will.
Okay. Cool. And we will come to that in a moment. And then we wrap up with a little summary and very cool. Very nice. We'll cover the future here in a sec. Very nice. Beautiful work, Matt. I want to thank you so much for walking us through your very awesome article.
Well, thanks for the opportunity. I appreciate it.
Yeah, thank you. Okay. So you hint at it, particularly there at the end and with some of the caveats. And so let me go ahead and ask, and where do you think we go from here, given the published article? Is there some perhaps optimization to do on the number of pixels? We talked about non-gravitational stuff. Yeah, just sort of next steps. Where do you think we go from here, given the published
Yeah.
article?
I mean, I think there's some room to lay out all the, the trade studies of, this is if you use this kind of HELPix grid, this is how much time it takes, and go all through all of that, incorporating non-gravitational accelerations,
Uncertainties.
incorporating
Yeah.
orbital uncertainties.
Right.
But from what I'm working on next, the next step for me is a project called Layup.
Okay.
Uh, and so that's, rebound, assist, layup, ha ha ha. Um,
For those of you who are basketball challenged, okay.
yeah. So yeah, my younger son is a basketball player, and he excels at assists. So anyway, so the next one, layup, is orbit fitting, right?
Oh, yeah,
So
yeah, yeah, yeah.
Yeah, so we have, here we've got this thing where we can say, this is where we're going to see this thing on the sky. We will have a bunch of data. We want to use the data to improve the orbit.
Yes.
And orbit fitting is old as Gauss.
Give me five and I'll tell you something.
Yeah. So, but doing that on efficiently for millions of objects like we're gonna, and billions of observations from Rubin,
Yes, yes,
you need good tools.
yes. Very good. Well, that'd be really exciting to see if we can get layup to rival the efficiency of some of these other pieces. So it'd be really cool to see.
Thank you.
Very nice. Very nice. Matt, thank you again so much for walking us through your very awesome article.
Been my pleasure. Thanks a lot.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.